So good afternoon, everyone. Welcome to this edition of the NITheCs Colloquium. Today it is a pleasure to introduce Dr. Cerene Rathilal. Cerene studied mathematics at UKZN, where she obtained her PhD in 2019. But she's now a lecturer in the Department of Mathematics and Applied Mathematics at the University of Johannesburg. And her area of research is algebra and topology, and Pointfree Topology is one of her specialties, I guess. Yeah. Cerene is also affiliated with the Center of Excellence for Mathematical and Statistical Sciences. She is a council member of the South African Mathematical Society. And she's also affiliated with NITheCs, and in fact, she's one of the principal investigators in our mathematical structures research program. Yeah? Just last week, Cerene started, in collaboration with NITheCs, revision classes for high school learners so that we can prepare them a little bit for their maths tests and exams. And she's also organizing the International Day of Mathematics celebrations in South Africa, which is an event that takes place, I don't remember the exact date now, Cerene, you will help me out, but sometime in the second half of March. Yeah?
19th of March.
19th of March. I remember it is a Saturday, but I forgot the day. Yeah? So on the 19th of March. So you will receive through NITheCs all the relevant information if you want to attend and participate in that event in 2 weeks or so. Yeah, Cerene, thank you very much for being with us today. I see you already started sharing your screen. You're most and welcome to start your presentation. Before I give you the the go ahead, sorry, I always forget to remind people to use the Q&A facility to ask questions. And since we're not so many, people are most than welcome to raise their hand at any time, and we will make a plan to give them the right to ask the question in person. Yeah, and after the talk, if Cerene has time, we will have again our little short virtual social event in Kumo Space, and I will share the link in the chat just now. Yeah. So Cerene, thank you very much for being with us this afternoon. You're most than welcome to start now. Thank you very much.
Thank you, Prof. Petrocione, for that very wonderful introduction. I appreciate that. So today I'm going to be speaking to you about Pointfree topology and some of the work that I have been doing recently. So as I've been advised, I thought it was wise to do this in 2 parts. And so in the first part of the talk, I'm going to be talking to you pretty much about the history and the beginnings of Pointfree topology and why we study it. And then in the second half of the talk, I will move on to some of the results that we've obtained on Wallman compactifications of frames. So the question is, what is Pointfree topology? So essentially, this is the study of topology without points. Topology without points says it simply as a slogan. And what we do here is that the primitive objects of study is the lattice of open sets rather than the points themselves. So one of the prime pieces of literature that I always refer students to is Topology Without Points, Frames and Locales by George Picado and Alesh Poltra. And so this is one of my go-to books. It is like the Bible for Pointfree topology. So Pointfree topology is also often referred to as pointless topology. And so I've heard numerous, what could I say, humorous things about it, or jokingly, lots of people like to say that it's pointless. But with this talk today, I'm sure that as we explore the topic, we're going to see that Pointfree topology is certainly not pointless in that subjective way. So let's talk about its beginnings and its origins. So the history of applying some type of algebraic approach to studying topology can be seen as early as 1914, when Hausdorff was amongst the first to use the notion of the open sets of a topological space as a primitive object of study for abstract spaces. So since then, it was then work done by Stone in the mid-1930s, when Stone worked on the topological representation for Boolean algebras and distributed lattices. Apart from Stone's work, the second person to pioneer some type of work which applied an algebraic approach to topology was Wallman. And what Wallman did was he used the lattice theoretic ideas that existed to construct his notion of the Wallman compactification. And so today we are going to be talking a little bit more about the Wallman compactification for frames in the second part of today's talk. So beyond that, there has then been a gap. And then towards the late 1950s, there was some really important work that was done by Resman and his student Benabau. And simultaneously, there was work done by Donna Papert-Strauss. And what they had done was, this was the sort of the first occurrence of viewing the category of complete lattices with some type of distributive property and maps which preserve finite meets and arbitrary joins. And so this was done by Resman, and he had referred to this body of knowledge. He referred to these objects that he is studying as local lattices. Now, Donna Papert-Strauss at that time had written her thesis, and I think she was studying at the University of Cambridge at the time. And so in her work, she had simultaneously developed results studying the same similar type of objects. Her thesis is actually regarded as one of the first pieces in point-free topology. So in 2019, she had actually visited South Africa, and she came and presented at UJ at our department. And so I had the very nice opportunity of being able to speak to her. And so one of the questions I asked was, why did we call the objects frames? And so she explained the notion of local lattices, but how that terminology could have been confusing. And then she went on to explain that it was Darker, who she had collaborated with since the 1950s to, I think, the mid-1970s. And so he was the one, Darker was the one who coined this term frames. And so since then, when there was a boom in this topic in studying topology, a historically geometric subject with an algebraic approach, so when this happened, we then referred to this generalization of topology as the study of frames or the subject of frames. So she also went on to explain that during this time, the 1950s and the 1970s, she had published a series of papers with Darker, but she noticed that there weren't many people reading it. And so I think at that point, she felt a bit discouraged. And so what happened was she had moved her attention away from the theory of frames or point-free topology, and she then went on to do work on other topics that interested her. But then it was towards the end of the 1970s when Isbell had published his seminal paper, Atomless Parts of Spaces. And in that paper, I think this was the turning point that really drew the attention of mathematicians from all around the world, because here we had seen that categorically, the category of these generalized spaces were behaving differently from topological spaces or classical spaces in a sense. And so this motivated people to then go ahead and do more work in point-free topology. So since then, there has been a lot of work that has been done to generalize concepts from topology into point-free topology, where we do this without points. And those people include the likes of Banaszewski, Poultra, Madden, Babalal, Dubé, and there's so many more. So I apologize if the name of someone important is not featured here, and that would just be my oversight. So I do apologize profusely for that, but the aim here was to just throw in names that had contributed to this beautiful history and to the beginnings of pure mathematics. And so today, and the beginnings of point-free topology. And so today, point-free topology is a very well-regarded topic that's studied broadly everywhere. And in particular, there is numerous mathematicians in South Africa that are active in this area. Some of them being my supervisors, who is Professor Babalal and Professor Pillay. Okay, so what is a frame? So let's start off with the basic definition. A frame is a complete lattice which satisfies an infinite distributive law, and it's stated below. So what this means is that we have finite means distributing over arbitrary joins. We typically would denote the bottom element of the frame by 0 and the top element of the frame by 1 to prevent any type of ambiguity. If there wasn't any type of ambiguity. So if we were working with more than one frame, so then we would denote that with a subscript. For example, in this case, it would be 1L or 0L. Okay, so what do the maps look like? So what's actually working on these objects, which are now frames? So we say that a map H from L into M, where L and M are frames, is a frame homomorphism if H is able to preserve finite meets and arbitrary joins. Okay, so that is the basic definition of the structure, which is a frame. It is a complete lattice with a distributive property. And we have the notion of a frame homomorphism. So what I'd like to now perhaps quickly...
Sorry, Cerene.
Yes.
There is a question in the chat, which might be, if you could address it right now, that could be useful. I think it would help the audience to explain what is the lattice. If you are planning to do it anyway later on, then disregard my question.
Okay. So we have to start off with a poset, meaning a set together with some type of relation that satisfies three properties: that it's reflexive, it is anti-symmetric, and it is transitive. So that poset, if it in addition satisfies another property, that for any subset of the poset, we could take the join of that subset would exist, then we call that, that would be a complete lattice. So what is a lattice? A lattice is a poset satisfying the property that for any pair of elements, we could obtain the join and the meet. Perhaps
okay.
Let me elaborate on this a bit more. Okay. So just to add to that, a meet is regarded as the least, the greatest lower bound, and the join that I had mentioned is the least upper bound. So what is this relation between topology and this lattice theoretic approach that I was referring to? So if I had to start off with a topological space, okay, perfect, that is working. So then what we could do is we could form the following poset. So I'm going to denote this by O of X. And what does this look like? So this is simply the collection of subsets of the topological space X, where those subsets were nothing but the open neighborhood. So U is open. Okay, and so we refer to this, well, so this is indeed a poset. We could check that it is. And it is a poset with inclusion. And we refer to this since it is indeed a frame. So this collection actually satisfies that definition that I had placed on the previous slide. So it satisfies the fact that that collection is a complete lattice, and it satisfies this property of the infinite distributive law. Okay, and so we refer to this as the frame of open sets of X. All right, so let's just say that I now have two topological spaces. So let Y and X be top spaces. Then we could then, okay, so if maybe I should just say X and Y too, because I'm going to start off with a map. Well, it doesn't make a difference, but right. So if I start off with these spaces and if we have a mapping, a continuous mapping from the topological space X into Y, so F is continuous. Then we could consider the following. O of F, and O of F would actually be a map from the frame of open sets of Y into the frame of open sets of X. And how does this mapping work? It would essentially take an open set of Y's and it would send it to F inverse of that set, which clearly would live in the frame of open sets of X. So it turns out that this mapping here turns out to be a functor from, this is working from the category of top spaces into the category of frames. And so we've got that functor. And what, so it has been seen that in the case when we're working with sober spaces, what we end up having is that these OFs here, these mappings, they always tend to be, they will always be a homomorphism. Sorry, they could always be linked to a homomorphism running from OY into OX. So that's in the case when we have this assumption of sober. And in addition, what this actually leads us to showing is that we have a full embedding of this category of sober spaces into the category of, okay, what word should I use now? The dual category of frames, since we have that the map here, the order has changed. So we call the dual category of frames the category of locales. But beyond that, we could also then define a functor from frame into top. And so I think I'm not going to go into the details of defining this because of the limit on time that I would have. But what I would like to say is that through the lenses of category theory and through the work of all of the giants that came before us, it is clear that Pointfree topology is a generalization of the study of topological spaces. And so we have, there are many notions from topological spaces that can be generalized into the subject of Pointfree topology. Okay, so let me go back to my slides. And so I think that is where I'd like to wrap up the end of the first part of my talk, where I gave an overview about Pointfree topology. And now I'd like to talk about some of the results that we've obtained, but perhaps I could add one more. What is the benefit of generalizing the theory? Surely we're not just generalizing it for the sake of a generalization. And so, as would have been seen in the seminal paper by Isbell, there are numerous benefits. One of them is that we could do things in a choice-free manner in Pointfree topology. So results, for example, which previously needed choice, may not necessarily need choice in the arena of frames, in the sense that we could now prove those results more constructively. A typical example would be Tikhonov's theorem. And so we can show that the product of compact locales of frames is compact without choice. And so that to me is really important. Okay, so going on to the new work. So today I want to talk to you about some of the work that was done on S-metrizability and the Wallman compactification of a frame. So if we're going to be talking about S-metrizability, then we need a notion. Well, this immediately implies that we're going to be talking about the notion of property S. So property S is a notion that was defined by Cerene, and this was studied in metric frames. So as we progress with this talk, I will then show you how we can generalize this into the notion of Pointfree topology and get the necessary generalization of property S. But what does it mean so what we're studying is we're going to be looking at S-metrizability of a metric frame. So once again, I'm using a term that I have not yet presented, but I will present it to you and answer that question in a few moments. So what we would be interested in doing is looking at when a metric frame would be S-metrizable. And the definition is as follows, that a metric frame in a sense, if just to give you an idea, is a generalization of the notion of metric space. So here we have that a metric frame is S-metrizable if and only if there exists a compatible metric diameter. So by diameter, this is capturing the notion of a metric from metric spaces. And so this compatible metric diameter must then have property S. If that's the case, then we have that metric frame is S-metrizable. So what I'm interested in doing is getting out other characterizations of S-metrizability of metric frames, utilizing the Wallman basis of a frame. And so this work was originally studied classically by Garcia Maynez. And so what we're doing is we are now generalizing this result into Pointfree topology. Okay, so in order for us to end up getting to what is the Wallman compactification, we first need to have an understanding of what is a frame compactification. And so let's talk about that first. So in order to get to a compactification of a frame, we need this notion of regularity and compact. So we say, firstly, before I get to regular, that if I have any two elements, so A and B, A would be rather below B, which is written in that way, if there exists some other element C, such that A met with C is the bottom, and B joined with C is the top. And so we then characterize a frame to be regular if any element in the, so if for every element in the frame, we could express that element as the join of all those members in the frame which are rather below A. Then we have the notion of compact. So a frame is compact if whenever any cover of the frame can be expressed, can be reduced to a subcover of the frame. And so again, that's in alignment with our understanding of compactness classically. So what is a compactification? So a compactification of a frame M is some compact regular frame L together with a dense onto homomorphism. So I think I might have skipped explaining denseness, but here is a definition of what it means for a frame homomorphism to be dense. We say that a frame homomorphism is dense if whenever the following property is true. So if whenever H of an element is the bottom of that frame, is the bottom element of M, then X itself is forced to be the bottom element of L. And so if that property is satisfied, the homomorphism is called dense. So in our definition of compactification, we have that we need a dense onto frame homomorphism from L into M. And so we denote the pair LH as the compactification of the frame M. Okay, so our approach to defining a Wallman compactification would be to do this in terms of a Wallman basis. And so this is also an approach that was studied by Rathilal. So before we talk about Rathil's approach, we need the definition of what is a Wallman basis generalized into Pointfree topology. So a Wallman basis of a frame is a subset of the frame satisfying three properties. The first is that the bottom and the top element of the frame must be in the basis, and that the basis must be closed under finite joins and finite needs. The second condition is that every element of the frame must be, for every element of the frame, we must have that that element A can be expressed as the join of all members from the basis which are rather below A in terms of the basis B. And so what does that mean? It's still written, so this rather below relation is still defined in the same way, it's analogous, except now that we are only working with elements, this element C must be an element that lives in the basis or the subset that we had started off with. So if that is the case, then we have this rather below relation with respect to the subset B. And thirdly, that whenever you have two elements in the basis whose join is the top, then we would find two other elements in that basis, in the subset, satisfying the property that their meet is the bottom of the frame, and A joined with C is the same as B joined with D, and it is in fact supposed to be the top. So if a subset B satisfies these three conditions, we call this a Wallman basis of the frame. So Babulal then went on to show that given any Wallman basis, he could obtain a strong inclusion. So why would we need a strong inclusion? That's because that in order for us to talk about a compactification, we're going to be using the approach I've forgotten the name, it'll come to me now, but we're utilizing this approach in which we associate a compactification to a strong inclusion. It was actually shown that the set of all compactifications of a frame is isomorphic to the set of strong inclusions on a frame. And so what Babulal did was he's using this approach. He defines a strong inclusion and then he generates a compactification. So what does this strong inclusion look like? So it is nothing but a binary relation on your frame. And in this case, we're starting off with a regular frame. And this relation ends up satisfying the following property, that A relates to B if and only if there exists some element from the Wallman basis such that that element can be sandwiched in the following way, that A is rather below C with respect to the relation on the Wallman basis, and C is rather below B with respect to the Wallman basis. And so it was then shown there's a few axioms that has to be checked, that would indeed be a strong inclusion. But what we require right now is to understand that we have this approach that would associate a strong inclusion to a Wallman compactification. And so this work is well known, and it was widely published and understood. And so essentially we get the corresponding compactification that's defined in terms of the Wallman basis because Babulal defined the strong inclusion on a regular frame in terms of the Wallman basis on that frame. And so we denote the corresponding compactification that we now obtain by gamma B of M. And so we call that the Wallman compactification of M. So what does this gamma B of M look like? It turns out that it looks like, or it's nothing but all the strongly regular ideals of the frame associated with that strong inclusion that Babulal had defined. And so correspondingly, we have a join map. This is a dense onto map because remember, this is the map that's associated with that compactification. And so gamma B of M together with the join map is actually the compactification of M. So Babulal then went on to show that if we have a Wallman basis And so, of course, we could generate its compactification and we could get this join map. So if we considered the right adjoint of this map and we denote it by K, so K would then be a map from M into gamma B of M. And then if I considered the image of the Wallman basis under the right adjoint, then it turns out, that K of B is also a basis for gamma B of M. And so this result is actually useful in some of the things that will follow. Okay, so before we get to talking about our characterization of S-metrizability in terms of the Wallman compactification, it is actually necessary for us to also generalize the following result by Steiner. So this is Steiner's result classically. Steiner says the following: you start off with a metric space that is compact, and then we could show that it has a base of open regular sets satisfying the following property. It's closed under finite intersections and finite unions, meaning that it is a ring of regular open sets. So we would like to generalize this in the Pointfree setup, so for frames. So of course, that generalization would have the statement. So now the metric space would have to be a metric frame. And so we would have that if I have a compact metric frame, then that compact metric frame would have a base of open regular elements. And it will turn out that that base is also going to be a ring of regular open elements. So we now need to define all of these concepts and ensure that they truly make sense. Okay, so I guess before we start talking about the notion of a regular element, it's important for us to talk about, well, what is a metric frame? Okay, so in order for us to talk about a metric frame, we would start off, so let L be a frame. And we're going to define a mapping. And we're going to let D be a map from L into the non-negative reals. Okay, such that the following axioms hold. So we have the first four axioms, M1 to M4. So the first property is that the map D must map the bottom element of the frame to 0. So these zeros are different. That's the real number, and that's the bottom element of the frame. M2 says that the mapping D must be order preserving. M3 says that whenever I have this disjoint meet, then the diameter, so I'm going to refer to this mapping D as a diameter, right? So then the diameter of the join of elements would be less than or equal to the sum of the diameter of those two elements. And M4 says that for any epsilon, the collection of all those elements of the frame whose diameter is less than epsilon forms a cover of the frame, meaning that the join of this set is equal to the top of the frame. And so if M1 to M4 is satisfied, then D is called a diameter. And if in addition, M5 is satisfied, then we call the diameter compatible. So what is this notion of compatibility? It says that for any element in the frame, so for each element in the frame, sorry, A can be expressed as the join of all those elements uniformly below A. And we define it in the following way, that this condition must now be satisfied. So if M5 is satisfied, I've got a compatible diameter. If M6 is satisfied, then I've got a compatible metric diameter. So M6 plus, of course, all of the things that came before it. So M6 says that whenever you take an element in a frame and an epsilon greater than 0, then the following must be true, that I would be able to find two elements less than or equal to that A, whose diameter is less than epsilon, satisfying this inequality. So if I have my frame L and my mapping D, and if D satisfies M1 to M6, then LD is called a metric frame. And so this is our generalization that was actually attributed to Coulter that generalizes the notions of metric spaces. So coming back to Steiner's result. So we now know that we can talk about a metric frame. We've already spoken about the notion of compact in one of the earlier slides. And so now we have to discuss regular. So it turns out that we have the corresponding notion, and we say that an element in a frame is regular if and only if A is equal to the double pseudo complement of A. So what is the pseudo complement of A? That I had not mentioned. So A star is the pseudo complement of A, and this is nothing but the largest element, B, such that B met with A is equal to the bottom element. So it is the largest B in the frame such that that is true. And so here, going back to the slide, we're characterizing a regular element as having the property A equals to the double pseudo complement of itself. Furthermore, we define this notion of a ring quite analogously. It's translated naturally, that for any two elements in the subset, if this subset is closed under finite meets and finite joins, then we refer to the subset as a ring of M. And so we are then able to get out the statement for Steiner's result and of course prove it. So the proof I have not included in here today, but the result that we are able to get is that if MD is a compact metric frame, then it is true that M has a base of regular elements, and that base is a ring. Okay, so this result of Steiner's will be important, but before I show you how it ties in, we need the notion of a dense metric sublocale. Sublocales can be thought of as generalizations of subspaces. So how do we define them? So we have to start off with a metric frame and a mapping. So we've got a metric frame L rho and a frame, an onto frame homomorphism H from L into another frame M. So what we're trying to define here is the notion of M together with some diameter being a metric sublocale of L rho. And so we do it in the following way. We define a diameter on M in the following way, that for any A in the frame M, we define it in terms of the rho diameter. And so it turns out that this diameter, so this definition of D is a compatible metric diameter based on the M1 to M6 that we had just seen. And so whenever this property is satisfied, that I could define a D induced by rho on some frame, then that M together with this compatible metric diameter D, we can prove that it's compatible and it's a metric diameter. This MD is then referred to as a metric sublocale of L rho. We would also need the notion of dense, and we say that MD is called a dense metric sublocale of L rho if one is satisfied, and if in addition to that, that homomorphism, that onto frame homomorphism is also dense. Okay, and so we now come to Theorem II, and Theorem II tells us the following, that whenever you have a dense metric sublocale MD of L rho, defined in that way, just as we had seen in the definition, and if I suppose that L is compact and B is a ring basis of regular elements of L, so this is where Steiner comes in, because I would not have known that this ring basis of regular elements would have even existed. So now that we start off with compact, we get out Steiner's ring basis of regular elements, and we can then show that H of B is in fact a Wallman basis of M. And so that's quite interesting. So utilizing this Wallman basis and going through that approach that we had seen earlier, we could generate a Wallman compactification in terms of this basis using the strong inclusion that Wallman had defined. And so we can then show that that corresponding Wallman compactification of M, so it's defined in terms of H of B, so we denote it by gamma H of B of M. It turns out that that's isomorphic to L, the compact frame that we had originally began with. So we've actually shown that for any compact frame, any compact frame would essentially have a Wallman compactification that was defined in terms of dense metric sublocales of itself. Okay. And so the next notions, I see I am pressed for time, but let's see how far we go, is the notion of, well, firstly, we're going to begin on a locally connected frame. What does it mean to be locally connected? It means that any element can be expressed as a join of connected elements. And we have this notion of a component of an element of a frame. And so a non-zero element is a component of some U and M if it is connected and it is maximally connected in U. We then require this understanding of insular to be able to review one of Wallman's results. And so if we have our Wallman compactification defined in terms of a Wallman basis, then of course we had seen that this Wallman compactification consists of these strongly regular ideals. So we say that an ideal in there is called insular if whenever X is an element of the ideal, then I could find a Y in the ideal, which has finitely many components, hence the necessitating that definition, such that Y is actually an element of the Wallman basis, and we have the strong inclusion property is being satisfied. So this here is supposed to be the strong inclusion with respect to the basis B. So I should have a sub B. So that's a definition of insular. That's what we needed. Wallman showed the following, that if you have a locally connected Wallman basis on a locally connected frame, then these conditions are equivalent. So in particular, we have that if every ideal in the Wallman compactification is insular, then it is equivalent to the join map being a perfect locally connected compactification of M. And so these are one of the important results that Wallman had published in his paper. I will reference this at the end. And this was also crucial in helping us obtain the characterization for S-metrizability. So before we utilize Wallman's result, we also need these two results on countability. In particular, we use proposition 4 to prove proposition 5. And proposition 5 says that if your metric frame is compact and locally connected, then every element of the frame has countably many components. So I've included the proof here because this is one of the shorter ones, but I will not go through this now because I think I have 10 minutes remaining or less. And so we get to Theorem 6, and Theorem 6 was one of the main results that we proved. And this was highly non-trivial to show. So this result says that a metric frame is S-metrizable. So what does S-metrizable mean? Let's go back. So I haven't spoken about property S yet. Right. So a metric frame is S-metrizable if there exists a compatible metric diameter row on your frame M, such that M row has property S. What does it mean for M row to have property S? Okay, so if I start off with a metric frame, then LD has property S if and only if for every epsilon greater than 0, we would be able to find, so there exists a finite collection. Okay, well, I'll just write it down. It's A1 to AN connected. So we have this finite collection of connected elements of L, satisfying the property that the join of all of these connected elements equals to the top element of the frame, and that the diameter of each of these elements is less than epsilon. So this is for I equals 1 to n, and that join is running from 1 to n as well. So this is the notion of property S. So if we could find if we could find a compatible metric diameter such that that compatible metric diameter together with the frame has property S, then the original metric frame is S-metrizable. Okay, and so this is where we were. And so we have the following result. Now, depending on that which I've previously mentioned, that MD is S-metrizable. Sorry, if MD is S-metrizable, then we have the following happening: that M is a countable, locally connected, and uniformly connected Wallman basis. So in proving that result, we actually required this theorem. I should have called like Theorem star, and it says that whenever you have a connected, locally connected metric frame, MD, then MD is S-metrizable if and only if MD has a perfect, locally connected, metrizable compactification. Okay, and so this theorem, which I'm just going to refer to as Theorem star, was utilized to prove Theorem 6. So now we come to the main result. And so the main result that we were able to show is the following. So it's the following characterization. And so if I start off with a locally connected frame, then it turns out that the following is equivalent, that M is S-metrizable is equivalent to M has a locally connected and uniformly connected Wallman basis. So we're seeing some relation to what was said in Theorem 6. And this in turn is equivalent to M has a countable, locally connected Wallman basis B, such that every ideal of that compactification is insular. And here I see some connection to what Bobelal had previously shown. So in order for us to prove this, so 1 implies 2 is obtained from Theorem 6. Sorry. Then 2, if and only if 3, is actually a result by Bobelal. And then it remains for us to show that 2 implies 1. And so there was quite a bit of work that had to be put into this. Again, this utilizes one of Bobelal's results and Theorem star that we've stated here. So the idea, in order to show 2 implies 1, so in order to show that M is S-metrizable, we end up showing that if MD was S-metrizable, so what are we working with here? So we show that M admits some diameter D and such that the metric frame MD has a perfect locally connected metrizable compactification. So that was the approach in order to show that 2 implies 1. And so utilizing all of that, we then obtain this result, Theorem 7, which holds true when the metric frame is locally connected. And so much of this work relied on Bobelal's work from this paper, Local Connectedness and the Wallman Compactification. Of course, Steiner's work, and Garcia Maynez, since we were aiming to generalize his characterization on S-metrizability. And so that is all that I needed to share today. So thank you for this opportunity.
Yeah, Cerene, thank you very much for the very nice talk. I think now it's the time to open it up for questions and comments. And I would like to encourage the participants, since we're not so many, maybe to raise their hand and we can give them the right to speak. Let's wait a second if we have some volunteer. Oh, Ilya, sorry, I didn't ask you whether there were questions in the Q&A or in the chat.
No, there was a question in the very beginning by Zurab, but that was about the. Okay, so we have a hand.
Okay, please. Voila, here we go.
Oops.
Sorry, Ilya, we did it at the same time. Please, Temba, you're also welcome to ask a question. Sorry, Ilya, that's your job. You go.
Thank you, Francesco. Thank you, Cerene. That was a very lovely talk indeed. You know, just a question, Ma. Have you had a look at what happens in the case of binary co-products by any chance? The S property, how does it behave with respect to binary co-products?
No, I haven't. I actually hadn't thought about that at all. Is there a paper that you could refer me to that could give me some background so I could think about it?
No. Even in spaces, no, I don't know much about the S property, even in spaces. Sorry. I thought maybe it's something that perhaps you might have thought about.
Okay, Prof, would you be open to me having a conversation with you thereafter?
Okay, then.
Okay, thank you.
Okay, thank you, Temba. See if there are further comments. Here we go. Please, you have the right to talk. You're most than welcome to ask your question in person.
Hello.
Yeah, hello, please, we can hear you.
Yes, Tuti here, and thanks for the nice talk. I just wanted to ask maybe it's a very simple question, or not even necessary. Regarding metric frames and the classic metric spaces, you said that the metric frames are a generalization of metric spaces. Is there some kind of a connection? Because, say, for example, you indicated that frames are a generalization of topological spaces, and you could indicate a direct link between the two. Thank you.
So I think what you were asking is how could we see the link between metric frames and metric spaces? And so what we would have to do is then apply this notion to the frame of open sets. And so we'd be able to see that those definitions are equivalent if we had to do that. So I'm not sure if I answered the question. I see this chat box as well. Okay.
Here's I'm not sure if the I think yeah, Temba is back. Please, Temba.
Yeah, just to add on what Cerene says, if you start with a metric space and then you apply this O functor, well, contravariant functor that she mentioned at the beginning of her talk, and then you form the completion of that in frames, then you apply another contravariant functor called the spectrum functor, you end up with the completion of the metric space. So you can realize the completion of a metric space very nicely via Pointfree topology. Thank you.
Thank you very much for that comment. Let's wait another second if there is a further question, Cerene. Okay, seems that our participants are very quiet this afternoon. But Cerene, maybe they are saving the questions for conversation starters when we meet again in Kumo space just now. So I think if there are no urgent questions, Cerene, then thank you so much for the very nice talk. I think even if I'm not a mathematician, I think I learned what the questions are that you are interested in. Thank you very much for that. That was really very nice. Thank you. Then also thank you to all the participants for being with us. And again, an invitation to chat with Cerene in a less formal environment in the other platform that we usually use. Yeah. So Cerene, thank you very much. We will hopefully see you just now in Kumo space. Thank you.
Thank
and
you.
If you're not aware, our load shedding has started again, or will start again in 4 minutes. so some of you might get affected just now by load shedding. Yeah. Okay. Cerene. Yeah.
Can I get the link to Kumo space? Sorry.
It's in the chat, and it should have opened in your browser automatically. So if you look in your browser, it should have opened there automatically. Yeah. Sometimes I forget to click that option, but today it worked out. Yeah. Okay. Thank you very much. We'll see you just now in Kumo space. And Ilya, thank you very much to you as well. Thank you. Thank you.